Okay, I wanted to help you with the block on the incline problem. So here I have my block and my incline with some angle theta. I don't know what it is, but let's take a look and see how we solve it. So we've got a couple of forces that have been described to us. One of them is the downward force of gravity, and the other is the force normal, or the normal force, normal to the plane of the incline going down. And it asks you for some other information. Now, on an AP exam, if we had our free body diagram and we were drawing our free body diagrams, we would not draw components. We wouldn't split things into components. We would only draw actual forces, but we do probably need to split something into components to figure out what some of these values are. What is the force normal and stuff like that. So what we're going to do is we're going to treat this force of gravity as the hypotenuse of a right triangle, and the right triangle has two legs or two sides on it. The first side here that is opposite to the normal force, this component is perpendicular or normal to the plane of the ramp. And since it is an adjacent side, if you look at this as being angle theta, then this also is angle theta. It's the adjacent side, so it's going to be equal to the mg, the force of gravity, times the cosine of theta. So the other force is, or component, is parallel to the plane. So that will be the force that is accelerating this box down the frictionless plane, and that force is going, since it's opposite to the angle, is going to be equal to mg times the cosine, times the sine of theta. And of course, the force of gravity is just equal to mg. So now we've got everything we need. Mg cosine theta is this force that's perpendicular. So the normal force is the same magnitude, mg cosine theta, but in the opposite direction. So the force normal is just equal to mg times cosine of theta. And that's all you need. Now, the resultant of these two vectors obviously is a force down, which is the thing which will cause this to slide down the ramp and accelerate as it goes down the ramp. So this resultant force that points down the ramp must be opposed by friction, which is pointing up the ramp in an equal amount. I'm not going to draw the resultant here because it's not a force, but I do know that it's going to be at right angles to the normal force. So this is the force of friction. Sometimes you'll see this as F of S, because this is the force of static friction because it's not moving. If later on we're going to talk about the force of kinetic friction. So if it's sliding down but friction is opposing it, that's kinetic friction. But when it's not moving, it's static friction. So I can call it S, F of S. So you may see F of S, F of K, or just FF for the generic force of friction. So these are the three forces acting on this box. These are the only three that we would be allowed to put on a free body diagram on the AP exam. However, you may break it into components as long as you do it on a separate drawing that is not the one for your free body diagram. They'll give you a nice big dot usually to draw your free body diagram, and these are the things you draw on the dot. The components, if you want to draw a picture and split it into a million components, that's fine. But there are really only three forces: the force of gravity, the normal force, and the friction force, which we found by calculating the resultant here, which is this guy, mg sine theta. That's this portion of the that's parallel to the plane which would make it roll or slide down the plane if it was frictionless. But in the equilibrium problem, it's not, so it's got to be opposed by that force of friction. Like that. Hope this helps.